Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. In this video we are going to continue from our previous video where we discussed critical points, computing maxima and minima, and we will study examples of computing maxima and minima. So let's quickly recall what we studied in the previous video. So we have studied critical points, saddle points and the second derivative test. So point A is called a critical point of a function f of x if either f is not differentiable at a or f prime of a is 0. A saddle point is a critical point which is not a local maximum or a local minimum, which means it is not a turning point. So remember, turning points are local maxima, which means a local maximum or a local minimum, and a saddle point is one where the derivative is 0, but it is not a turning point, or it may not be differentiable. Okay, so suppose f is twice differentiable, then we had something called the second derivative test, which we can apply to check the nature of the critical points. So if a is a critical point and f double prime of a is positive, then a is a local minimum. If a is a critical point and f double prime of a is negative, then a is a local maximum, and if a is a critical point and f double prime of a is 0, then the test is inconclusive. So let's look at some examples. So let's apply it to these examples and see how to use the test. So let's look at x cube minus 12x. So of course this is a nice function, so you compute f prime x. So f prime x is 3x squared minus 12, set it to 0. So setting it to 0, we obtain 3x squared minus 12 is 0, which means x square is 4, which means x is plus or minus 2. So these are your critical points. So critical points are plus or minus 2. And now let's check what happens to the double derivative. So what is f double prime x? So f double prime x is 6x. So f double prime of 2 is 12, which is greater than 0, and f double prime of minus 2 is minus 12, which is strictly less than 0. So what does that mean? That means, so therefore 2 is a local minimum and minus 2 is a local maximum. So that is what happens for this function x cube minus 12x. Let us look at the function cosine of x. So for cosine of x, well, we repeat the same thing. So f prime of x is minus sine of x. What are the zeros? So of course sine of x, we know what are the zeros. So they are multiples of pi. So equating to setting it to 0, the critical points are all points of the form k times pi, where k is in the integers. So now let us check out of these which ones are local maxima, which ones are local minima, and which ones are saddle points. So for that, let us compute what is f double prime of x. So f double prime of x is minus cosine x, and let us check this for k times pi. So f double prime is minus cosine of k times pi, and now this depends on the parity of k. So if k is so this is so cosine of 0, cosine of 2 pi, these are all 1. So minus of that is going to be minus 1. So if k is an even integer, or the other way of saying this is if k is congruent to 0 mod 2, and it is 1 if k is an odd integer, right. And what does that say? That says that the local so k times pi, where k is even, are local maxima, and k times pi, where k is odd, are local minima. Okay, let us do this last example. So, here well, let us differentiate. So, you get f prime x is 3x squared plus 2x minus 1. Okay. So, this looks somewhat complicated, but it is a quadratic. So, if I set it to 0, I know what the roots are. Setting it to 0, we obtain, so 3x squared plus 2x minus 1 is 0. That means roots are, so minus b, so minus 2 plus or minus root b squared, so 4 minus 4 times a times c, so 4 times 3 times minus 1, so that is minus 12, so 4 plus 12, and then divided by 2 times a, so 2 times 3, so that is minus 2 plus minus root 16 divided by 6, so that is minus 2 plus minus 4 divided by 6. So, the roots are, so minus 2 minus 4 by 6 is 1 root, so that is minus 1, and minus 2 plus 4, that is 2 by 6, so 1/3. So, these are the two roots. Let us check what happens to the function at these roots. So, these are your critical points, minus 1 and 1/3. So, to see if they are local maxima or local minima, let us set this to, let us compute what is f double prime x. So, that is 6x plus 2. So, evaluating this at minus 1, we get minus 6 plus 2 is minus 4. So, this is a local maximum. Local maximum. And if you evaluate it at 1/3, we get 6 times 1/3 is 2 plus 2, which is 4. So, this is a local minimum. Okay, so, I hope the method is clear. So, this way we can check what are the local minima and maxima. Okay. So, it should be pointed out that sometimes the double derivative test does not work, that is what we saw. So, if it is inconclusive, you have to really work harder to find out which ones are local maxima and minima. Okay. So, before we go to closed intervals and so on, let us ask why does it work. Okay. So, why does this test work? So, let us see what is happening to the tangents as we come close to this point here. Okay. So, let us look at this, and yeah. So, as we vary this, the tangent is going to vary in a small neighborhood of that point. Okay. So, let us see how this goes. So, you can see the tangent is slowly varying, and as it comes here it becomes 0, meaning horizontal, f prime becomes 0, and then again it changes. So, what happened in this entire part? If we start again, initially this derivative value was negative, then it became 0, then it became positive. Okay, this is what happened. So, when you have the double derivative, the double derivative will be positive, because this is an increase, because f prime is increasing, right, and we have plotted f prime as well. So, let us stop this. We have plotted f prime as well, and let us check that phenomenon is occurring here. Indeed, as you can see, f prime is increasing over here all the way until you get to some intermediate point. Okay. So, and you can see what that intermediate point is. That is exactly where here it is concave upwards, and at some point it changes and becomes concave downwards. So, that point is where the double derivative becomes 0. So, here is n2, here is a slider n2, and as you can see, this is a small, if we choose a small neighborhood around this point, then the tangent, so at this point the tangent is not, we have a problem. So, you have to choose a small neighborhood. So, if you choose a neighborhood which is minus 0.61 from that point to something ahead, we will be fine. Okay. So, let us play this animation, okay, and now it changes. So, this is why you have to get a local, this is local. So, you have to choose a small interval around this point, then it will be strictly decreasing, and the graph at this point of f prime bears this out, right. This graph is decreasing at the point A. Okay. So, that is why the f double prime is negative, and the same phenomenon happens at this point. So, let us stop that, and now look at this third one, which is what happens at 0. Okay, so, let us, okay, so for 0 we will see something strange is happening. So, now let us play that animation again. Here it is decreasing to 0, and as soon as it hits 0 it starts increasing again. Okay. So, it is not strictly increasing or strictly decreasing around this neighborhood of 0, and that is why the f double prime over there is 0. Okay. So, I hope these pictures have been illustrative of what we had in mind. So, let us go on and study local maxima or minima on closed intervals. So, sometimes we want to find the local extrema of a function on a closed interval a comma b. So, in that case, in addition to finding the extrema via the previously discussed method, which means to find f prime a, set it to 0, f prime x, set it to 0, and so on, it is possible that the endpoints could also be local extrema, and so we have to consider them separately. So, let us consider this example of f of x is x squared on the interval minus 1 comma 1. So, in x square is minus 1 comma 1, if we compute the first derivative, this is 2x, set it to 0. So, I think it is clear, of course, that what is happening at 0, it is a global minimum in fact. So, f double prime of x is 2, so f double prime of 0 is 2, therefore, it is a local minimum. Yeah, in fact, it is a global minimum because we know how the graph of x square is. But if you want to consider it only on this interval, then minus 1 and 1 are also local maxima. Why is that? Because if you look at the graph of the function x squared, it is something like this, and if we want to look at it only in the part between minus 1 and 1. So, on that part, this is it, right, and so this point here, which is minus 1, and this point here, which is 1, are actually local minimum and local maxima, because in a small neighborhood around those points, remember now neighborhood means only you are considering only points which are within minus 1 comma 1. So, they will be local maxima. Okay, so, for closed intervals you have to also consider the endpoints separately. Okay, how about global maxima or minima? So, sometimes we want to find the maximum or minimum value of a function on a particular interval I, and here by maximum or minimum we mean the global maximum or minimum. Now, this may not exist in general. So, sometimes it may and sometimes it may not. So, for example, if you take the function 1 by x on the interval 0 comma infinity, it has neither a global maximum nor a global minimum. Why is that? Because this function approaches infinity as you come close to 0, and it approaches 0 as you come close to infinity, but it never attains the value 0, nor does it ever attain the value infinity, obviously, because it is not a real number, and so it can never attain a maximum or minimum value. Okay. So, in general, maxima or minima, meaning global maxima or global minima, may not exist. So, in this case actually there is no local maximum or local minimum either, but here is a fact: if the interval I is closed and bounded, so closed means you include the boundary points, and bounded means you do not go to infinity. Yeah, you have to be within some a comma b, and the function f is continuous. So, this is important. Then the maximum and minimum must exist. So, note that the maximum and minimum are in particular local maxima or local minima, unless they are on boundary points. If they are on boundary points, then they need not be a local maximum or a local minimum in the sense that we have studied before. Okay. So, to find the maximum and minimum, we find the critical points and the boundary points and check the value of f on all of them. So, we can in fact do this on any function which is defined piecewise continuously with finitely many pieces on a closed and bounded interval. So, let us do an example of this just to get a clear picture of what one is saying. So, in this example, f of x is x cube plus x square minus x plus 5 between 0 and 100, and it is x cube plus 2x squared plus x minus 5 between minus 100 and 0, and we want to find, let us say, the global maximum or the global minimum. So, let us see how to do this. So, first of all, we ask what are the boundary points. So, here the boundary points are 100 and minus 100, and we have to also include 0 as a boundary point, because that is where the definition of the function changes. So, here we include 0 as the boundary point, and then let us compute what are the critical points on each piece. So, remember that when we are computing critical points, say I want to compute what is the critical points for the first piece, that is x cube for the function x cube plus x square plus minus x plus 5 between 0 and 100. This is within the open interval 0 to 100. So, when we differentiate and put this function to 0, we may get several critical points which are not inside this open interval. So, we have to only take those which are inside the open interval 0 to 100, not even the boundary points. Okay. So, let us write down what is f prime x. So, f prime x is 3x squared plus 2x minus 1, that is if 0 is strictly less than x is strictly less than 100, and it is 3x squared plus 4x plus 1 if minus 100 is strictly less than x is strictly less than 0. So, now let us put these to 0 and find out what the critical points are. So, on the first piece, the critical points that you get are so let me do that computation here, because remember that I don't want to take all critical points, but only those which lie in that interval. So, this is a quadratic equation. So, to solve this equation, so we want to find when 3x squared plus 2x minus 1 is 0. So, we know how to solve quadratic equation. So, the solutions are minus b plus minus root b squared minus 4ac by 2a if the equation is ax squared plus bx plus c. So, that gives us minus 2 plus minus root 4 minus 4 times 3 times minus 1 divided by 2 times 3. So, the two possibilities are where we have minus 2 plus minus root of 16. So, that is 4 divided by 6. So, this is either minus 4, 2 minus 4 which is minus 6 divided by 6. So, that is minus 1 or minus 2 plus 4 which is 2 divided by 6. So, 1/3. But now as you can see, minus 1 is not in the interval 0 to 100. So, I should not take that as a critical point. So, one of the critical points is 1/3 coming from the first part. For the second part, let us do a similar computation and see what that yields. So, there I have to find the roots of 3x squared plus 4x plus 1. So, that is minus 4 plus minus root of 16 minus 4 times 3 times 1 by 2 times 3, and so computation is similar. You get minus 4 plus minus root of 16 minus 12 which is 4. So, root of 4 is 2 divided by 6. So, again the answers here are minus 4 minus 2. So, minus 6 by 1. So, minus 1 or minus 2 by 6. So, that is minus 1/3. Okay. So, both of these are inside the open interval that we are considering. So, this is minus 1/3 and minus 1. Fine. So, now we have these 3 critical points and we have our 3 boundary points 100, minus 100 and 0. And so, now we can evaluate f at all these points and see where the maxima, find out which of these are maxima and minima. And when I mean maxima and minima, I mean global maxima and global minima. Okay. So, what is f of 1/3? So, f of 1/3 is 1/3 cubed plus 1/3 squared minus 1/3 plus 5. So, that is 1 by 27 plus 1 by 9 minus 1/3 plus 5. So, that is 1 plus 3 minus 9 plus 5 times 27. So, that is 135 by 27. So, then that is 139 minus 9. So, 130 by 27. So, close to 5, slightly less than 5, between 4 and 5. Okay. And then we have f of minus 1/3 and you will have a similar computation. So, in the end you are going to get minus 1 plus 3 minus but here though I have to use the second equation. So, this 3 is multiplied by 2. So, minus 1 plus 6 minus 9 and then minus 135 by 27, and again that should give us something close to 5 or rather minus 5. So, minus 135 plus 5. So, minus 130 minus 139 by 27. Okay. So, it is between minus 5 and minus 6. and then I have f of minus 1. So, if I substitute that, we get minus 1 plus 2 minus 1 minus 5. So, that is minus 5, and then we have f of 0. So, f of 0 is 5, and then finally, we have f of 100 and f of minus 100. So, f of 100 is 100 cubed plus 100 squared minus 100 plus 5. So, I am not going to compute this value because it is obvious that this number is really large as compared to the other numbers, which are all in the range of 5 or minus 5 or between minus 10 and 10, and this number is of the order 100 cubed. So, this is clearly a huge number. So, this is certainly larger than all of these others, and similarly if we have f of minus 100, then that is minus 100 cubed plus 2 times 100 squared minus 100 minus 5, again of the order minus 100 cubed. So, this is in absolute value this number is very large. So, with a negative sign it is the smallest number amongst all these, and so that gives us that this is the first one, which is 100 is a global maximum. So, let us write that down. So, this number here is a global maximum, 100 is the global maximum, and then we have minus 100, which is the global minimum. So, minus 100 is the global minimum. Yeah. So, amongst all possible values taken by the function, the one taken by minus 100 is the smallest and the one taken by 100 is the largest. Okay. We can also go ahead and ask about these critical points, what kind of points they are, local maxima, local maxima, local minima, or saddle points, and to do that we have to compute f double prime. Again, this has to be done only on the open intervals 0 to 100 and minus 100 to 0. So, if you do that, you will get something like 6x plus 2 and 6x plus 4 for the respective intervals, and then by plugging in the values you can check whether they are positive or negative, and hopefully they are non-zero, and then you can check if they are local maxima or local minima using the second derivative test. Okay. So, let us end with this warning example. So, if you have f of x is x to the power 4, clearly 0 is a global minimum, but what happens, I mean what does our test give us? So, if you, so in particular it is a local minimum. So, we hope that it will show up in the test. So, if you do 4x cube, then f prime of then the critical point is 0. So, now we do the double derivative test. So, that is 12x squared, and when you apply it at 0 you get 0. So, in fact, the double derivative test ends up being inconclusive. So, inconclusive, right. Although this function is so clearly and obviously is a function which you can clearly and obviously analyze, meaning what are the global minima, the test is inconclusive. So, you have to be careful that when we end up in this inconclusive situation, you may still have a local, in fact a global minimum or maximum. So, that you have to analyze by different methods. Okay. So, let us quickly conclude by recalling what we have done in this video. We saw the second derivative test, which is which tells us that if at a critical point the second derivative is negative, then it is a local maximum. If it is positive, it is a local minimum, and if it is 0, then it is inconclusive. We saw that the inconclusive situation can occur because of local minimum, local maximum, or saddle points, any of them, and to do that we have to really check what happens to the derivative function close to that point. Further, we saw that if you have a closed and bounded interval or you have a piecewise continuous function, then you have to check the to get these phenomena of local maximum and local minimum, you have to also check the function values close to the at the boundary points or at the break points where it is piecewise defined, and only from there can you conclude about local or global minimum or maximum. Thank you.